Here is a chemical reaction, and I am telling you how much of the substances we have before the reaction happens. 4.6 moles of methane and 5.4 moles of dioxygen, and none of the products. How much reactants and products do we have after the reaction? This is the question we want to figure out. We need more information. There are two scenarios. In the first, I give you one more piece of information. For example, I could say that 2 moles of methane react. The way I write this into the table is the following. Into the change row, I would write -2 mole for methane. We need a negative sign because when a substance reacts, it is used up. Positive change means the amount increases, negative change means the amount decreases. Okay, so we entered how much the amount of methane changed as some of it reacted. This additional piece of information allows us to fill in the remainder of the table. We can fill in the entire change row if we know just one of the values. For every column, we can fill in a missing value if the other two values are known. Let's do the change row first. If 2 moles of methane were used, 4 moles of dioxygen are used because they react in a ratio of 1 to 2. We know that because substances react in stoichiometric ratios, given by the stoichiometric coefficients found in the balanced chemical reaction equation shown at the top. Likewise, we can figure out that 2 moles of carbon dioxide and 4 moles of water are produced. Now that we completed the change row, we know the initial amount and the change in amount for every species, reactant or product, in the reaction. Now we can add the change to the initial amount to figure out how much of each species we have at the end. So at the end we have 2.6 moles of methane, less than initially, and 1.4 moles of dioxygen, also less than initially. If we start out with no product, we will have 2 moles or carbon dioxide and 4 moles of water after the reaction, which is more than we had initially. So I told you how much methane reacted, and you were able to figure out all the values in the table. Instead, I could tell you how much methane is left over at the end, say, 3.2 moles. Again, you can use this information to figure out all the values in the table. You would first determine the change of the amount of methane, then all other changes, and then calculate the missing value in the end row. Watch carefully as I fill in the table. Again, notice that the changes for reactants are negative and those for the products are positive. As the reaction proceeds, bonds between atoms are broken and formed, using up reactants and forming products. The small green numbers in the change row give an example. For every 1 mole of methane and 2 moles of dioxygen used up, 1 mole of carbon dioxide and 2 moles of water are formed. You can quickly check your calculation by comparing the green numbers with the numbers you entered into the change row. At the beginning, I said there are two scenarios. Here is the second scenario, which is called the limiting reactant problem. Instead of telling you, for one species, how much reacts or is present at the end, I just say the reaction goes to completion. This means it goes as far as it can, until at least one of the reactants is used up. In the animation, I am combining as many methane and dioxygen molecules as I can. As soon as a reactant is used up, the reaction is done, even if other reactants are still present. This is different from a race, where the race continues even after the first runner reaches the finish line. In a chemical reaction, you need all reactants, otherwise you are stuck and the reaction will not proceed. The reactants that run out are called limiting. The reactants that are not used up are called in excess. In the animation, the dioxygen was limiting. There was 1 molecule of methane left, but it could not react because it was lacking dioxygen as reaction partner. In a limiting reactant problem, you first have to figure out which reactant is limiting. Once you know this, you can fill the entire table. I will show you 2 ways to proceed. The first one is indirect, and I am showing you this way to get a feel for this kind of problem. The second way is direct, and is the most efficient way to solve a limiting reactant problem. The indirect way is basically trial and error. Let's assume that methane is limiting, and see if our results make sense. If it does, we are done. If not, we will have to erase everything and start over, this time assuming that dioxygen is limiting. Okay, we will try if methane is limiting. Limiting means that all of it is used up. We have 4.6 moles of methane, and to use all of it, we have to write negative 4.6 in the change column. Adding up the initial and the change amount, we get 0 for the amount of methane at the end, as expected. What about the dioxygen? Methane and dioxygen react in a 1:2 ratio, so we would need 9.2 moles of dioxygen. You might already see the problem, but let's fill out the entire column for dioxygen. The change is negative 9.2 moles, and adding that to the initial 5.4 gives negative 3.8 moles for the amount of dioxygen at the end. This is a nonsense result. It is impossible to have a negative amount of a substance left over. Another way of saying that is that we run out of dioxygen before we run out of methane, so dioxygen is limiting. We have to erase everything and start over with dioxygen as limiting reactant. If dioxygen is limiting, all of it will react. The change will be negative 5.4 mole, and at the end, we will have nothing, or 0. What about the methane? Methane and dioxygen react in a 1:2 ratio, so we would use up 5.4 mole divided by 2, that's 2.7 mole of methane. We will write negative 2.7 into the change box, and when we add up initial and change amount for the methane, we see that 1.9 moles of methane will be left over when the reaction goes to completion. In other words, methane was present in excess. This was the indirect, trial and error way of figuring out what happens when the reaction goes to completion. Luckily, there were only 2 reactants, so we just had to test 2 possibilities. The direct way is much more, direct. It requires a fast calculation on the side. You can do this calculation under the ICE table, but here we will use another, much simpler table. I will call it the limiting table. We just need the information on the reactants, specifically the initial amounts and the stoichiometric coefficients. For methane, the initial amount is 4.6 moles, and the coefficient is 1. For dioxygen, the initial amount is 5.4 moles, and the coefficient is 2. For each reactant, you divide the initial amount by the coefficient of the reactant. In this case, we obtain a value of 4.6 moles for methane and a value of 2.7 moles for dioxygen. Whichever reactant gives you the lowest value is the limiting one. In this case, it is dioxygen. With this information, you go back to the ICE table and fill out the column for the limiting reactant, dioxygen in this case. You might want to start by putting 0 as the amount of dioxygen at the end of the reaction. Everything else follows from that as we have done before. We first complete the dioxygen column by entering negative 5.4 moles into the change column. Then, we can fill all the other boxes in the change row. Finally, we can calculate the amount present at the end of the reaction. As expected, there is some methane left at the end because it was present in excess.